afternoon. This is CIVE632, Computational Hydraulics and Hydrology. And today is November 1st, 2021. And this is the first class of the 11th week. So we are making progress. The last week is the 16th week. So we have 6 more weeks to go on this course. The subject today is more on roll waves, the theory as well as the practice, and we intend to cover 3 papers today. The first one is the classical paper by Montuori from Italy. Then the paper that Porras and I wrote in the year 1995, 1996. And then the other paper, which is an applied paper that myself and Marcela Diaz wrote in the year, I believe, 2015. So we have a bit of everything. We have a classical paper, then a theoretical paper, and then a practical paper. Hopefully, in the next 75 minutes, we'll be able to cover everything, all 3 of them. So hold on to your chairs. This is going to be tough. There's a lot of math in here and very intricate math. And yet our math is totally different than anybody else's math. First of all, we'll take a look at Montuori's, which is somewhat different than Caraya's as well as Vedernikov's. Our treatment kind of simplified their treatment because they were focusing on the cross-section and on the friction. We instead chose to focus on the concept of celerity of the kinematic wave as opposed to the dynamic wave, which is the deal. It's the subject that we really dominated. So that's understandable that we came up from that angle in order to really simplify this problem. But by the way we entered or got into the calculation of the inherently stable channel, that got really, really complex. We, of course, followed the early work of Liggett, professor at Cornell University, without whom we would not have done our work. I've always pursued somebody else's unfinished work. I already told you that. But we did a good job, good mathematical job, always in conjunction with the work of our students at San Diego State University. So the first thing I'm going to do here today is I'm going to briefly discuss, I'm not going to cover all the subjects. As I already told you, I do not believe that if there's a paper out there that we should read in order to understand everything. I don't think that that's a possibility. We pick and choose in the paper what we feel that we can at that time understand. Besides, I do believe that the Montuori paper is somewhat dated. He did it in 1963, I believe, 1960 or 63. He originated in Italy. I believe he's a professor out there in Italy. It's dated. We have a better answer. So why should we dwell on stuff that is dated? So the subject, let me just get over here. The subject of the Montuori paper is this one. Can everybody see it?
Yes, we can see it.
Okay. The subject is, like I said, I'm going to go over this paper briefly. I intend to spend maybe 15 minutes on it. The title is Spontaneous Formation of Wave Trains in Channels with a Very Steep Slope. I don't read Italian. Italian is kind of a little bit somewhat like Spanish, about 70 to 80% Spanish, but still they have some words in there that are kind of hard to understand. So let me just go. I read this thing this morning, and I'm hoping, of course, I don't have a PowerPoint for this or anything. But he's saying in here that you may be able to control the roll waves if you kept the discharge low. Actually, around here he says it. Well, I'm not going to be able to read the whole thing by looking for the stuff. I should have underscored or underlined this. But the point I'm trying to make in here, and you guys could read this on your own later on, is that he says that we may be able to design a channel in such a way that we can contain all roll waves. But that's not quite true because we've seen that these waves were not contained in the Bolivia experience. So as you can see right from the start, Montuori is making an assumption which is not correct. And I think I already told you many times these papers are supposed to be at the top of our knowledge, and yet they do make some mistakes. Nobody's free from mistakes. Okay, he also does say something that it was new to me. He said that the formation of wave trains have been known for some more than a half a century. He's talking 1884. Um, I'm not quite sure because I have not researched fully the situation whether GMA was working with the channels in Switzerland, the Swiss channels, or whether this was a subject that was independent, or this paper here, 1984, which I have not read, is independent of the work that Cornish did in the year 1907 when he published that famous photo, which I believe, or it's been referred to as being the earliest picture of a roll wave event in the literature. So so let's move on here. He is coming up with equations, which most of these equations we already are familiar with. 1 and 2 we're familiar with, and 3 and 4. There's variations, and it is amazing how this subject can get to be readily very complex because it could be seen in different ways. The fundamental issue here is the one that was presented by Kraya. Let me go to page 6 here. Is the one that was presented by Kraya uh, in the year 1952. He said that these roll waves will happen when the kinematic wave celerity exceeds the dynamic wave celerity, which is correct. Um, in normal flow, before it becomes unstable, the dynamic wave celerities, the Lagrange celerities are fast and they go ahead, and the kinematic wave celerity is slow and it goes behind. But until you get to the Vedernikoff number equal 1, after Vedernikoff number equal 1, the kinematic waves come out fast and they actually coalesce, or I guess you could say reach out and get the dynamic wave celerity. And at that point, that's when we experience from theory and from practice the formation of this roll waves. I still don't 100% understand why is it a train of waves. I think I already mentioned to you that this is a characteristic of dynamic situations or dynamic systems. Okay, in page 8, he is mentioning something like this over in page 8. He's coming up with this equation 7 or 7 prime, in which he's saying the fruit number is gotta be greater than 3/3, 3/2. This 3/2 has a lot to do with the Seddon speed in here. Okay, so we interpret this 3/2 to be right there, the Seddon speed for Chesi formula. So as you can see, the Seddon speed is coming up as it should in this treatment, because we're basically, whether we realize it or not, we're comparing the two phenomena at the extreme of our S-curve, the kinematic waves on the left and the dynamic waves on the right. As I think I mentioned to you, it was my knowledge of the S-curve, which was unbeknownst to these people that have been writing prior to the 1970s, that allowed me to really dig in and understand these concepts that could be very obtuse, very complicated. And then the math came in later out of persistence. We wanted to do it and we felt that we could do it. And we, of course, did spend a lot of time doing this. It was years of effort. Professor Ponce, as you know, has been at San Diego State for now 41 years. It is a lifetime. So we've done quite a bit of work, and a lot of it has been very good work. But I mean, it is persistence. It's a lot of persistence. Perspiration, as they say, not so much inspiration. So we have in here now we're in page 10, and in page 10 it mentions this formula also, and over here the 2 comes up. The 2 comes up with Chesi friction. So as you can see, this gentleman Montuori is coming up with all sorts of arguments, one after the other, in a very confusing manner, I must say. He didn't have a whole lot of order in his mind. But he did it, and he has become very popular because he was translated into English. And he was saying a few things that at the time people thought were important, like the Montuori length. He said that the waves will develop if the channel was long enough. I mean, that's correct, but that's not the truth. That's not complete truth. The complete truth is that the waves will develop under a certain size waves. Only certain size waves will develop. So it's not so much that they will develop if the channel is long enough. It is that some of them will develop and some will not. And I think that Montuori missed. So to me, the length of Montuori is not a falsehood, but it is something that is really unnecessary because the probability or rather the creation of roll waves, it's going to depend a lot on chance. It's a stochastic issue whether they'll form or not. It'll depend on the conditions at the entrance because you have a channel. There's going to be an entrance to the line channel because prior to the water entering the line channel, it was not hydraulics. It was hydrology. It was upstream. And upstream there was no line channel and there was no roll waves. no no roll wave ever occurred in an unlined channel, in a natural channel. The Bolivians paid for this. They had natural channels and they never had a roll wave. They'd never seen a roll wave. But when they started paving it and lining it up in order to carry it in carry a large wave under somewhat orderly fashion, they actually messed up because they brought forth or produced the roll waves. Okay, so so that's page 8, page 10, in page 16 in here. I read this morning. In page 16, we have, okay, now he's coming up with the conditions of V, equation 16 double primes. It says V. So he basically is taking a lot of pages to say the Vedernikoff greater than 1 is the condition. And then he says dimensionless quantity V is called Vedernikoff number by the Russian authors. I am not quite sure because I have not read the entire Russian literature. But as I understand it, this paper was published in the year 1945. And then in the year 1948, only 3 years later, Powell, writing in the US, said, this is a new concept. It's a good, interesting concept and practical, I mean, not practical, but important concept for design of channels. And I believe I could call it, I think he said, we might as well call it, or we could call it the Vedernikoff number. So christening the concept as Vedernikoff number, I am not sure. I thought it was Powell, but according to Montuori, uh, the Russians, maybe even earlier, I don't know, were already calling it the Vedernikoff number. One way or the other, Vedernikoff got to be famous. And famous because he worked on a concept that he's getting credit for and that parallels that of the Fruit number. The Fruit number was created around 1871 by Fruit. Actually, that story has been told in the literature. Fruit did not create the Fruit number. He created something similar, but that's another story. We'll leave that for later. For those of you that haven't heard the story yet, because I believe I talk about that in my class, in my open channels class. Okay, so we're now uh, then he talks about what they call it, and he says, well, there were, here it is, in 1904, look at this, early. Committee for the Study of Surface Waves submitted a report to the British Association concerning observations made on 2 torrents, and these are in Switzerland. So the British were looking at the Swiss channels. Committee proposed to give the name roll waves. So that is the origination of the term roll waves, which I think I already told you that in Spanish does not translate really well because it would be like rollo, ondas de rollo, like roll waves, and that doesn't quite make a lot of sense in the Spanish language. So people in Bolivia started calling it the pulsating waves, which is a little bit more physical because they do pulsate. They come in periodically. Yeah, I'm not quite sure how well it sounds in English though. But whatever it is, it's all a semantic. We know what they are and how they are produced. As to what we call them, I mean, it's important, but uh, but it's a semantic problem what we call it. Besides, we call it what other people call it. We kind of follow the tradition. If we want to change it, it takes a lot of effort to change things once they become established, even though they may be wrong. I mean, look at what Danny Fred did. Danny Fred was, well, let me not get in there because we'll spend a little time, which is unnecessary at this point. And you heard me talk about that already, about the fact that Danny decided to use the word dynamic for the waves that were mixed kinematic dynamic. Okay, so we are in here now, 22nd over here. He's coming up with a bunch of equations and tables and so forth that he or other people put together. He's obviously talking about cross sections. And we know that that's the fact. And we will clarify that later on with very simple equations. We didn't have to do a whole lot of theory like on practice as he has done to show that in fact it is correct, the fact that what we're saying is correct. Okay, the equation 18, page 22, right. Uh, he comes up with the realization that the ratio of the depth over the hydraulic radius greater than 1.4 will eliminate the rollways. See, rollways no longer occur. So that's a pretty good finding, I think. See, if the objective is to eliminate the rollways, you got to make the channel deep. That's simple, right? Because H is the depth. The depth R has to do with cross section and stuff, which is true, by the way. It may not be 1.4. Because this is kind of an approximation. There's a gray area in there. But that is true. We already know that to be true because the greater the H in relationship to the R increases the beta. Excuse me, decreases the beta. And when we decrease the beta, we end up with a condition where the rollways start to disappear. So I agree with what he's saying. I may not agree exactly with his number, or the rationale why he said it, but I know exactly what the rationale is because we have measured and we will, for the homework, we will measure the betas. They're very simple to measure, okay? And we will determine that is the fact. Okay, so that is it. So on page 26 in here, as you can see, I'm jumping because I don't believe that we should stress or read every sentence that he wrote. There's a lot of stuff here that is, I'm not going to go superfluous, but it's really not to the point that we're trying to deal with here. So page 26, page 26 he says something about that it is impossible to predict the waves, and he's talking about the length of the chute in order to avoid the waves, or to produce the waves. And like I said, Montuori is famous for his length of the channel at which that is required for the waves to be produced. In other words, he's saying that if the channel is short, then the waves will be arrested. They will not produce. And like I said, he may be okay, but he's not looking at the whole story. The whole story has to do with stochasticity, meaning the chance that the certain size of perturbations will be there at the entrance of the channel or not. If those sizes are too small or too large, they will not produce the roll waves. Only the waves in the middle will produce the roll waves. We know that from our theory, from our S-curve theory. Okay, and finally, I'm just going to finish in here. I already have 15 minutes here. And so he goes on and on to talk about it, mentioning a whole lot of people. He must have spent a whole lot of time writing this paper. And finally, in page 35, he says something important. He says the cross sections with narrow base will avoid roll waves. He's correct there. See, through experimentation, they have found a whole lot of things. So he and others have found a whole lot of facts or truths, but they failed to put it all together in a coherent theory, which we have done. And I'm going to be talking about that right after this paper. And finally, on 36, on 6, he says something that is true, completely true. He says the wave trains will not occur below for Vedernikovs less than 1. If you measure correctly the Vedernikov less than 1 and you have Vedernikov 0.99 or 0.98, you will not see the roll wave. Okay? So we stand by our original statement that says that the condition for the roll waves to develop is Vedernikov greater than 1. But it's only necessary. It's not sufficient. The other condition is that for certain sizes of waves, which depend a whole lot of the conditions at the entrance and how it's raining and when and how the rain produces, by collecting the rain in runoff produces the waves. So it will depend the size of the entering wave. Some sizes will have a tendency to amplify and some will not. Well, technically, the ones in the middle will amplify, and the middle is based on slightly on the fruit number. We have already discussed that last week with the Meissner paper. So I'm going to stop in there with this paper, and I'm going to come on to the next one, and I do plan to spend 30 minutes on this, at least 30 minutes. This is a very complex paper. Let me move this up over here. Okay, is everybody seeing the green here?
Yes.
Okay, cool. Okay, so Pedro Porras came to me in the year 1993, I believe, and he wanted to do a master's thesis. He said his dad was at the time, we're talking 1993, that's 28 years ago. His dad was at the time, I'm not sure if he was a professor or a practitioner of hydraulic engineering in Venezuela. His family is originally from Venezuela, so he was here for a master's degree. So I at the time was interested in following the work of Liggett, whom I have met in 1975 when Liggett presented his paper over at Colorado State University. And I thought that was such a weird subject that I thought I would never get into it. And why should I anyway, right? I said that in the year 1975. But to my surprise, then 25 years later, 75, 95, right, I was looking at this very carefully. Because it all came down to the issue of the importance of the Vedernikov number, which I thought for a long time, even today, that had not been given a fair chance in the hydraulic world or global hydraulic engineering literature. People mention Fruit all the time, but they mention Reynolds also, but they do not mention Vedernikov. And Chow didn't do that either. So I thought I would fix the slate, by coming up and saying that Vedernikov was, in our theories of hydraulic engineering, as important as Fruit. Okay, and we succeeded in doing that, and we believe that it's coming up. It's not there yet, but it will be coming up. I would like to see 90% of hydraulic engineers know about Vedernikov instead of what it is right now, which is probably less than 10%. Okay, so let's take a look at the abstract. The effect of cross-sectional shape on free surface instability. Yes, that is characterized by the dimensionless relative kinematic wave celerity. Celerity, dimensionless, relative, kinematic. We know the kinematic wave celerity, but not the relative or the dimensionless. So they're kind of related. Defined as beta minus 1. Beta is the important number in open channel hydraulics. Beta is the exponent of the normal discharge flow area rating. The value of C sub drk is a function of the type of friction, yes. So we have to specify or specialize to Manning or Chessy. And the cross-sectional parameter delta, which I believe was developed or invented by Vedernikov in his paper, the exponent of the wetted perimeter flow area relation, because we need to characterize or parameterize in some way the shape of the cross-section. And this formula is very good at it. P equal Ka to the delta. So delta becomes the parameter to characterize the shape of the cross-section. Okay. A stable channel is defined as that which features a constant delta. Two types of stable channels are formulated: unconditionally stable, for which delta equal 1 and the Vedernikov numbers equal 0 for all fruit numbers, and conditionally stable, for which delta less than 1 and Vedernikov less than 1 for fruit numbers in the range f less than or equal to a neutral stability fruit number. So why are we making these things that complicated? Well, let's take a look. Liggett designed the first channel, unconditionally stable, for all fruit numbers. And he stopped there. I don't know why, but he did stop there. But we realized that that was kind of a pie in the sky channel, because the Vedernikov is always going to be 0. But it's 0 for all fruit numbers. Fruit number 1,000, fruit number 10,000. And we should not be really talking about that, because the fruit number 10,000 is an idealization, is impossible. No channel was ever designed with a fruit number greater than 25 or 30 because of the issue of friction. The friction has a bottom, a floor. You cannot get 0 friction. Therefore, you cannot get fruit number 100. So the highest fruit number, the most likely value of the largest fruit number you could possibly calculate would be around 25. 25 is a good practical number. But even if you push it up to 30, it's no big deal, but not more than 30. And you can do that calculation easily with a slope and a friction. A certain slope and a certain friction will give you a certain fruit number. And I do believe that those of you that took open channel hydraulics with me, I had you do the calculation, even in an exam. Because you know the Ponce equation, it has an F and S of O and then the fruit number. So you have an F and S of O, you get the fruit number. And since you cannot have S of O 0, because it will not be a channel, you cannot have a fruit number infinity. Okay? So, since we had that situation, then it occurred to us at the time we were doing this with Porras, that what we should do is design a conditionally stable channel, which is not as wide as the one proposed by Liggett, but it still does the job, because it assures that you will not have roll waves up to a certain number. You can choose the number, say 25. So up to 25, you will not have roll waves. If you get up to 30, then you may, but then you're never going to get up to 30. So it was a practical thing that we came up with. In addition to this, I mean, everybody knows that in order to publish a paper, you got to come up with something new. If it's not new, it won't be published. That's a fact. Right or wrong, that is a fact of life. So I figured with Porras, that if we develop the conditionally stable channel, that it will be something new that nobody had ever done. So we did publish this paper in 1995. Okay, so let me move on in here with the subject in here. The subject has interested several researchers, beginning with Veternikov. I may be off a little bit in there. I was reading this today. It may be that the concept was discussed much earlier than Veternikov, but nobody ever know how to nail it down analytically. And it was Veternikov who was given the credit for doing that. And since the mathematics, the conjunction of mathematics and physics is always good, it's a plus, then I think we're fine. We're justified in giving the credit to Vedernikov at this time. Developed the criterion bearing his name. He did not call it Vedernikov. He just said, this is a number that will work for this condition. Then later on, other people came and gave it the name, or ascribed it the name of Vedernikov. The Vedernikov equal 1 describes the condition of neutral stability. Stable flow attenuates disturbances, while unstable flow does not. So unstable flow may promote the development of roll waves and steep channels. In addition, if you have a large channel, high Vedernikov number flows, flood waves may steepen to the point at which they become kinematic shock waves. So I was really extending even this theory of the roll waves to the kinematic shock waves that become killer waves, because it's the same concept. You get enough out there, lack of steepening, and then you will develop the killer wave, which we already talked about. Graya came and contributed in 1952 which we read last week, enhance the Vedernikoff criterion by interpreting it as the ratio of relative kinematic wave celerity to relative dynamic wave celerity. And then I'm going to be presenting a whole lot of equations in here. It's going to be kind of fast. You will have to reread this stuff in order to pick it all up. We don't have, obviously don't have the time, but it's there. It's written in there, and you will have to study it for later knowledge, for usage, the exam. We're going to have a homework out there, the next homework in about a couple of weeks. So you will have a chance to review this subject. So the relative set and speed, standard stuff. The equation 2, the exponent of the rating. Note that we use the word beta in here, or the symbol beta in here. I like the word beta, alpha, beta. Other people don't call it beta. They call it M, they call it N. It's confusing. Here we introduce the subject, we call it beta. Even though there was going to be some confusion in there, I guess we don't have enough familiar Greek letters to do this sort of thing. So then we have the small amplitude or Lagrange celerity. You heard me talk about this extensively. The definition of the fruit number. When we combine this whole stuff, we end up with 6. 6 is correct. I just checked it this morning. It's all correct. Then, therefore, the dimensionless relative kinematic celerity is beta minus 1. So this is the expression, a simple expression of Seven's law. The Manning equation, we already know. And then when we come up with, okay, the delta, where's the delta? Oh no, assuming a cross-sectional shape function P equal Ka to the delta. This I believe to be, presumably, Vedernikoff's contribution. Come up with this simple power function that will relate the perimeter with the area. And it is a simple power function. But I guess it works. I mean, I guess you could put another function more complex in there, and then you'll have to throw in some different things. But the point is that this function it has worked since Vedernikoff, and therefore, but this is a kind of complicated, well, no, actually I should say at this point that when we combine all these equations, we end up with celerity, dimensionless relative kinematic Manning equal to 2/3 of 1 minus delta. Okay, so we have in here, based on this equation, P equal K times A to the delta, we can come up with 3 asymptotic cases. Asymptotic cases, I call it asymptotic. I have not called it here asymptotic, but I do say that in my book. Asymptotic means that you get to the point where everything approaches that number, right? So the first asymptotic cross-section in open channel hydraulics is the hydraulically wide channel, for which delta is equal to 0. When delta is equal to 0, the weighted perimeter is a constant, and therefore there is no change in stage with the weighted perimeter. I mean, that's of course an idealization, because it'll never happen in practice. But if you have a very large channel, I mean a wide channel, it could be approximated. There are some wide channels out there. Some of the channels that transfer a lot of sediment have a tendency to have a shape of width over depth equal to 100, which you could not find otherwise in nature, but yet there are there. The case 2, the triangular channel, that is very commonly used in urban drainage, in highway drainage, urban and highway drainage, for which delta is equal to 1/2. And case 3 is the inherently stable channel. This is the one that we introduced, confirming or complementing the work that Liggett had done in the year 1975, the inherently stable channel. I came up with the word inherently stable. Liggett called it the stable channel, but I wanted to emphasize that this channel was stable inherently. That is why we call it inherently stable. For when delta is equal to 1. When delta is equal to 1 over here, the perimeter over the area is a constant, is equal to K. Perimeter over the area is a constant. So what channel would give you a constant with a perimeter regardless of the stage? The answer is the inherently stable channel. Okay? From these cases, it is inferred that, and this is a little bit, we had to think about this through, believe me, we spent a lot of time on these things. Oh, probably a week or 2 or 3 weeks, Porras and I trying to figure out all this stuff. But we did eventually figure it out. I told Boris we had to do it, otherwise he wouldn't graduate. But we did it both. I mean, I should say, we sat down, we discussed it, we spent a lot of time, and we did it. The conventional definition of Vedernikov is 11, in which he defined, the x was defined as this, which is a frictional function for both laminar as well as turbulent. And we should say, as I already shown to you in graphical video form, that the Vedernikov number is not limited to turbulent flow. It's also applicable to laminar flow. And under laminar flow, the fluid number doesn't need to be 2 for the Vedernikov to be 1. You can get Vedernikov 1 for fluid number 0.5. And that's because of the difference in friction between laminar and turbulent. Remember, turbulent is 1.5, laminar is 3 under Izard overland flow conditions. So we have the situation where, okay, so, but we're mostly interested at this point in the flowing channels. In the flowing channels, in channels, big channels, I mean channels properly mentioned or properly established is typically turbulent. In order for you to have turbulent flow, all you need is a couple inches. If it's less than half an inch, or then it could be laminar. But by the time you get to the float gets to a couple inches, already turbulent. I mean, from the standpoint of Reynolds number and so forth. So most channels out there will run turbulent flow. In order for you to run laminar flow, you'd have to have a situation like I shown in the video, where you have very thin laminar flow, or flow, not laminar, sheet flow over a highway or a road. And then at that point, it would become laminar. Okay, so so the dimensional relative kinematic wave celerity is V over F. Now in here we introduce something important. We say for V equal to 1, the fluid, we call that the neutral stability fluid number. That means that the neutral stability fluid number is always the reciprocal of the relative kinematic wave celerity. So now we're going to do stable design, stable channel design. And in here, I am going to I cannot go into detail. If I went into detail, then we'll spend 3 hours on this. So I'm just going to kind of go over it, talking about the most important things. I don't expect you to clearly, I mean, get into this whole thing. It is a very thick subject, and I'm not going to quiz you on it, but you should know where it came from. Besides, at the end of this class, we're going to do a calculation, and the calculation is an online calculator, and it's all done. Everything is done. Like, you don't have to go back to it, okay? So type 1, an unconditionally stable channel for which delta is equal to 1. This is the inherently stable channel. And type 2, a conditionally stable, which we're introducing in here, for which delta is less than 1. This channel features CDRK greater than 0 and FNS less than infinity, which is the way it should be. From the beginning, I realized that the Liggett channel was an idealization. And by the way, it has never been built. And my contention is that the inherently stable channel has never been built. It probably will never be built. But that doesn't matter. It does not stop us from pursuing the truth in the theory. Because from the inherently stable channel, we came up with a theory to solve the conditionally stable channel. We would have never gotten to the conditionally stable channel if it had not been for the inherently stable channel. Excuse me, let me check my WhatsApp in here. No, not yet. Not yet. I'm expecting a personal call or personal message today. That's why I've got my stuff in here. Just a second. Okay, fine. Okay, so again, so these are the equations that Liggett was putting together in his paper. These are the equations, and we follow through that. And the solution for these equations is analytic. Analytic, meaning it can be solved analytically. So we were able to do that. Okay, and we solve for the channels, and here they are. So if you look at these channels, they're compound channels. you have a base flow channel and a flood channel. Well, we call it base flow and flood just because it really is the difference between a small stage and a large stage. Small stage, more or less corresponding to base flow, and large stage corresponding to the flood channel. It is not, we're not saying that every time you overflow the small channel, you're going to get a flood. No, it's just a way to talk about it, base flow and flood. Okay, so what do these cross sections show is that in order to get a fruit number for neutral stability equal to 100, you need to have a very wide channel. But for lesser fruit numbers neutral stability, you can um, you can narrow the channel. Not a whole lot, but you can still narrow it. For 5, for instance, you get there, and this is for 3.5 depths of 0.5. But if you get depth on 75, you get a lot narrower, which is what you want to do. You don't want to use a whole lot of land to put the channel together. Although I must say, quite correctly, that we took out a lot of land, stole from the land, and made the narrow channel. That's what happened in Bolivia. Bolivia had a wide channel, it never had a roll wave. But then they cut it to 1/10, and now they've got a roll wave. The same thing happened in Tijuana. Not with the roll waves, but the same thing. The Tijuana channel was 1,100 meters wide before the development of Tijuana. Then when they would develop Tijuana maybe 50, 100 years ago, they cut it all down, and then they narrowed the channel to, I believe it's 100 meters. I could be wrong on the last figure. My memory is not perfect. But it's about the ratio from 10 to 1. I know it's 1,100 to start. Okay? No, 70. It's more than that. So they cut the channel from 1,100 to 700. I'm sorry, to 70. Oh, how'd they do that? Well, the only way they could do that is by increasing the depth. Because when the river flowed at 1,100, it was very shallow. But now that it flows at 70, it's very high. So increase the depth, put a bunch of levees on the sides, and that's it. You solve the problem. Right? They solved the problem. No, they didn't. They just came up with a solution, which is not going to work all the time. Because if the flow ever goes over the levees, it will kill a lot of people. While prior they didn't have any levees, nobody was killed. Everybody just run away from it, and that's it. So that is the problem with levees, a problem that, of course, we're not here to discuss. That's something that we could do perhaps in environmental hydrology and so forth. But these are the channels. Okay, and I do reiterate, the inherently stable channel, to my knowledge, has never been built and probably never will. But the conditionally stable could be. One second. Okay, I just cut it off because I can't answer right now. Okay, the conditionally stable channel could be designed because it is a solution, is a way to solve this problem. There's other ways to solve the problem, which we're going to talk about next week, but I'm not this week, Wednesday. Okay, so then we come in here, and now I'm going to explain in here how to design the conditionally stable channel. Okay, and these are the equations following from the work of Liggett, and we have this equation also. The extension of equation 18 to the conditionally stable channel leads to this. And this is the crux of this thing, or the important thing. Unlike 19, which is the Liggett equation, which can be solved analytically, 23 cannot be integrated analytically. The shape of the upper subsection T star may be obtained by numerical integration. Anytime you cannot do an analytic integration, you can always do numerical integration. That's what we did in here. We used a computer in order to do analytical integration. So we did that, and it was very complex, difficult to do, but we have done this all along, so it was not difficult for us. It will be difficult for you when you read this and figure out exactly what went on. So we have all this stuff in here which shows the way we did the computation, and then I'll clarify for you in the next paper. The effect of cross-sectional shape was shown to be characterized by the dimensionless relative kinematic wave celerity, beta at -1, in which beta is the exponent of the equilibrium or normal discharge flow area rating. 3 cross-sections are hydraulically wide, triangular, and inherently stable. The value of C sub drk is a function of the cross-sectional parameter delta created by Vedernikov, which is the exponent of the wetted perimeter flow area relation. Then we talk about a stable channel and a conditionally stable channel. We've already discussed that. Results show that the larger the initial hydraulic radius for a given fluid number for neutral stability, the narrower the resulting stable cross-section. That means over here. Right here. The larger the depth over here for 1, it's much narrower the cross-section. It's much narrower the cross-section. Okay. Stable channel is defined as one featuring constant delta and C sub drk. Unconditionally stable channel, which is the Liggett channel, and conditionally stable, that is R channel. Results show that the larger the hydraulic radius, the narrower the resulting. Okay, we went back to that. Likewise, the smaller the choice of fluid number for a given R sub O, the narrower the resulting stable cross-section. In other words, we could design for 10 or for 20. For 10, for fluid number of neutral stability equal 10 or 20. 20, of course, would be safer, but it would be more expensive. It would cover more area and so forth. So if you as a designer decide that 10 is high enough, it's extremely hard to get a fluid number more than 10. It's not impossible, but it's hard. Okay, it is almost impossible to get a fluid number more than 20 or 25. That we know because we touch the bottom of the friction. The friction cannot go below a certain number. Lucite, for which the Manning's N is 0.008, is the lowest friction possible, and that's lucite. It's a laboratory channel. It's not a real world channel. So you run into this bottom floor in here where you cannot go any further. Okay, a stable yet relatively channel may be designed. Such a channel should be largely free from roll waves and kinematic shock waves, provided the fluid number remains in the range. Right. Additional research is necessary to experimentally verify the findings of this study. Actually, I should delete the statement because you can't experimentally verify this stuff. It will just be so costly that I don't believe anybody will do it. So maybe this last sentence is unnecessary. I put it in there because Professor Ponce knows how to write a paper, even though, oh, that's right, this paper we did publish. You got to write a paper in a way that you provide something, always something new or some look into the future, because if you don't, then they'll cut you. Okay? That happened to me before. So we put in there, let's do some research, let's employ somebody out there to verify it. Even though it's largely a pie in the sky thing, but we did it that way. Okay? So now that I've revealed you most of my secrets, I am going to finish in here. Where am I? I'm going to get rid of this. I'm still working with this. Okay. So that's a Pedro Porras paper. So now we go to the paper by myself and Marcela Diaz. Marcela Diaz came to me in the year 2016, and she wasn't going to do a thesis, but she was going to do, like everybody else at San Diego State Civil Engineering, she has to do a project. What's the difference? A project is a 4-month thing, and a thesis is a 12-month. So the thesis is worth 3 times more in terms of units and so forth. So some people decide to do thesis, some others feel that they don't have to. You don't really have to. So they decide that they have to do the project. And I should tell you, for your information, that it was about that time, I think it was the year 2013 or 14, that the faculty changed the rules of the game and provided this project option. Prior to that, it was not an option. You didn't have to do research. You just had to do plan B. Plan A thesis, Plan B without thesis. And the Plan B was too soft on the students, and so the faculty they decided one day we sat together and decided that we were going to change the rules because we didn't like the Plan B. Basically, that was it. Among them, myself. And we came up with this Plan B, which is a different Plan B. Plan B, no thesis, but you have to do a project, which I believe is good. And has allowed the students to gain some research experience while the faculty also gained some benefit from it, right? Had it not been for this project thing, maybe Marcela would not have been there and I would have written this paper because, you know, I always need the students to write the papers. I mean, not to write the paper, but to work on the papers so that we can have something to do. So the inherently stable channel with online computations. So I got 25 minutes to discuss this. So the inherently stable channel, this is more on the subject that Porras and I did. Only that Porras and I was very theoretical, going all the way to the initiation of this thing with the works of Edernikov and others in Liggett. Here with Marcela, we were trying to do more practical stuff. So the inherently stable channel are reviewed. And its conditionally stable alternative, now we already know. They are reviewed, elucidated, and calculated online. The asymptotic neutrally stable cross-section or fruit number for the inherently stable channel is infinity. Theoretically, such a channel will become neutrally stable when the fruit number reaches infinity. Since the latter is a physical impossibility, this requirement effectively guarantees that the inherently stable channel will always remain well below the threshold, regardless of the flow discharge, thus completely eliminating the possibility of roll wave formation. The inherently stable channel will never achieve the value of fruit number which characterizes it. Therefore, constructing an inherently stable channel provides an unrealistically high factor of safety. This suggests the possibility of designing instead a conditionally stable cross-section for a suitably high but realistic fruit number such as 25, for which the risk of roll waves, I can tell you 25, I feel extremely comfortable with 25. I don't think 25 will ever be reached. I should say that with a grain of salt. Maybe it will, but it's not likely, like 1 out of 1,000. It's a risk that readily you could run, for which the risk of roll waves will be so small as to be of no practical concern. Okay, so let's move on in here. The inherently stable channel is that for which the asymptotic neutrally stable fruit number reaches infinity. And this is repetitious a little bit from what we did with Porras. So I'm going to go kind of fast in here. Okay, the requirement, the latter fruit number equal infinity is a physical impossibility. The requirement effectively guarantees that the inherently stable channel will always remain well below the fruit number, the threshold of Edernikov. As its name implies, an inherently stable channel is unconditionally stable. In a seminal paper on hydrodynamic stability, Liggett noted that the theory of the inherently stable channel had not been experimentally verified. That's where we get our ideas. He said, this is nice, beautiful, but nobody's ever done it. To the authors, nobody's ever physically constructed it to prove the theory with practice. You know, a lot of people say, if you don't show it to me physically, I don't believe it. And they could continue to say that. But that's okay. I mean, it's good practice, but sometimes we can't do it. Like in this case, it's too expensive, it's impractical to do it. Who's going to pay for it, right? So to the author's knowledge, the inherently stable channel has never been built. Yeah, we come out right and say it. We're not shy about that. Yet, theory tells us that it may be an effective way of avoiding roll waves. In certain hilly geomorphological settings, urban drainage may demand the construction of large steep channels. That's the case of Bolivia. Why Bolivia? Why are we mentioning Bolivia? Bolivia, the capital of Bolivia is La Paz, the city of La Paz. I don't know how many millions of people, but at least 2-3 million people out there. And they're all living in this hole. Excuse me for saying that, but it is a hole. If you haven't been to La Paz, you haven't seen the hole. I've been there. I was there recently twice. That was in year 2019, prior to the pandemic. I haven't been there again because of the pandemic. They had a bad pandemic. They're coming out of it now. The minute they are safe from the pandemic or vaccinated or whatever, I'm going to head out there again because we need to continue. We need to find out where they are. I have a whole bunch of friends out there. The point is that why Bolivia? And the answer is, imagine a hole, just a hole. it's not really a hole, it is a gully. A gully is a depression. In the case of Bolivia, the depression is about, I'm not going to say I know the number, but I'm calculating that it's at least 150 meters, the hole. Okay? And don't get me on that number because I never actually looked at it, but it's deep. It's a deep hole, deep gully. But the gully, like all gullies, has a way of coming in. You got to get into. It's not really a whole complete hole, but there's a depression, a gully, right? And then there is an entrance to the gully. But the entrance to the gully, for sure, for certain, has to be steep. Otherwise, you can't get in, right? So that entrance is where these channels are located. They're typically 5, 6, 7% channels. And 7% is already steep because I told you already 1% is already supercritical. Theoretically, under a condition of fruit number equal 1 for a slope of 0.005. So slope of 0.01 is already largely supercritical. So if you get slope of 0.05 or 0.06, it's already supercritical. As a matter of fact, we know that the fruit numbers are on the order of 2 or 3, or actually even 4 in that case. Particularly when you have a line channel, the fruit number goes up because the velocity increases and so forth. Okay, so at this channel's rate flat stage, the risk is high that the flow will become unstable. The following video shows we don't need to do that. We already seen that video. The recurrence of these pulsating waves in channelized rivers have been documented by Molina. Molina is my contact out there, the gentleman that sent me the videos that you have seen. I forgot his last name the other day, but Molina, he's a professor out there at the University of La Paz. At the time we did this, he was a young man, not anymore. It's been 25 years, okay? And he did write a very good paper, which by the way, I did publish it. Let me see that, yeah. Only that it is in Spanish. So in order to read the Molina and several authors, by the way, some French people are out there. Look, there's 3 or 4 French people. Why are the French involved in this? Because the French had a program with Bolivia where they were going out there to help them, universities and so forth. Okay, so that's the Molina paper, which, in case you're interested, it's a very good paper. It got me into this subject anyway, got me also interested. So we review the theory of the inherently stable channel, clarify its physical and mathematical basis, and develop an online calculator. We, of course, specialize in developing online calculators. The complexity doesn't matter. The speed doesn't matter either, because as you will see when you try this calculator is so fast, it's unbelievable. Even it's PHP, working on PHP, and it is fast. Now, I'm going to show you an output in Fortran, so you will wonder and you'll say, how come Professor Ponce, having the beauty of PHP, will do the Fortran? And I have a trick. I'll explain to you later why I did that. Okay, the theoretical background. Criterion for the instability is new to Vedernikov. Powell gave this criterion the Vedernikov number. I also have the paper by Powell in here in case you don't believe me. This criterion, which I am calling the Vedernikov number. That's what Powell said in 1948, okay? So we believe, based on this record, that Powell invented the word or developed the word Vedernikov, the recognition to Vedernikov. I'm sure Vedernikov never thought that he was going to become famous. People don't do these things to become famous because it may not happen, by the way. So you got to be lucky. Luck is the word. Machiavelli said that luck is 50%, and I agree with him, okay? So Vedernikov was lucky. There was Powell out there that was reading this stuff. If Powell had never read that stuff, maybe we would be called something else right now. But Powell came out and said it outright. I haven't heard this thing, and I'm going to call it the Vedernikov number. He obviously didn't know Vedernikov. He just knew that he had done it, right? So that's the way credit comes, by the way. Largely by luck, but you got to be there. But being there does not guarantee that you're going to be recognized. You could as well not. Okay, so raw waves are a train of waves, and we show here the Cornish article, which is a very good paper, a good picture. Never mind the sepia, that's Photoshop. I love Photoshop. We do work on Photoshop every single day of the year. Okay, it is tremendous. It's a very good, great program. So we put in a sepia in there because we wanted to give it a little age, you know, it looks a little aged picture. 1907 is already 114 years old. So we got another roll wave in here. These formulas you are all familiar with already. I don't need to repeat that. It's all repetitious. But in here, this is also repetition, but this bears repeating. It's also part of my work. For Veternikov greater than 1, the flow becomes unstable, opening up the possibility for the development of roll waves. Ponce and Meissner have shown that the condition Veternikov 1, equivalent to Froude number equal or greater than 2 under Chezy friction, is necessary but not sufficient, that it may not always lead to roll waves. Also, Montuori said that, by the way. And Montuori knew from experience that sometimes you have, sometimes you don't have it. And we have seen that also in channels. We have seen steep channels with no development of roll waves. Okay? So Ponce and Meissner showed that the disturbances would amplify within a relatively narrow range of dimensionless wave numbers, near the peak of the positive log decrement function. This is part of our S-curve, one of the 4 figures in my S-curve theory. Okay, and since this is the first time this function ever came about, nobody before could have understood or imagined that this could actually happen this way. How do we believe that this is the truth? It is the truth. It comes from mass and momentum. And mass and momentum, if mass and momentum is not right, then we're not right at all. We might as well fizzle. Okay, mass and momentum. We arrived at this equation. Okay, discussion. Since we are publishing this on the web, we have the freedom to do whatever we want. That's a good thing about it. The bad thing is that we may not get any respect, but that's another story. Okay, let me just say that in the discussion that we said this. In the linear stability analysis, Ponce and Simons confirmed the findings of Leichert and Whittam, that the flow disturbances would amplify when the kinematic wave exceeds the dynamic wave. Furthermore, Ponce compared the transport of mass and energy across the dimensionless wave number, concluding that Veternikov greater than 1 kinematic waves would overcome mixed kinematic dynamic waves, and that in turn the latter would overcome dynamic waves. Since kinematic waves transport mass and dynamic wave transport energy, it is readily seen that the overcoming of energy waves, right, mass waves, must lie the true nature of roll waves. We do believe this 100%, because that's the way it happened. So the Froude number, the definition combining equation underscores the significance, and we already discussed this. So now we're going to go in here a classification of all cross sections into asymptotic results or asymptotic values. The feasible range. This gives rise to 3 asymptotic cross-sectional shapes. Hydraulically wide with beta equal to 5/3 under Manning, for which the weighted perimeter is theoretically a constant. Triangular with beta 4/3, for which the top width is proportional to the flow depth. It's a triangular channel. And inherently stable with beta equal 1, for which the hydraulic radius in the upper subsection, the overflow subsection, is constant and equal to that of the lower subsection, of the hydraulic radius of the lower subsection, and through a number of neutral stability equal to infinity. And we have in here 3 graphs to show visually what we're talking about here. At the time we did this, I had a student, Nicole, who had worked with me. We did studies with Nicole. You've heard the Nicole paper. Nicole was a great mathematician. And at the time, she told me she was going on vacation to visit the Mississippi River. And I said, Nicole, do me a favor. When you're out there, take a picture of the Mississippi. Because I had not been. I've actually, yes, I've been on the Mississippi, but it was afterwards. No, I take that back. I was in the Mississippi in the year 2011. Yes. But it was not really the real Mississippi. It was over at the confluence with the Ohio. It was not the real Mississippi. So I didn't have a picture. So she got a picture for me over at Mud Island, Tennessee, Memphis, close to Memphis. So I put it in there because the Mississippi is a wide channel. Its depth could be maybe 30 to 40 feet, maybe 50 feet, a little more than that, but its width is like a couple of miles or something like this, or even if it's a mile, it is wide. So that's a wide channel. A mile is 5,200 over 50, so that's 1 in 100 ratio. This is a triangular channel and our inherently stable channel. Well, the work we did with Porras. Okay, so assume the existence of a lower limit imposes a practical limit, and for that we use our famous Chesi, dimensionless Chesi formula, and which is in my book also. Suffice it to say at this point, and I think I said this before, that this formula is very easy to find. I mean, very easy to figure out, but it's not used, unfortunately. They use the Chesi formula, which is not, they talk about the Chesi formula, but hardly anybody uses it. Poor Chesi. Hardly anybody uses the Chesi formula. Everybody uses the Manning, which is complex and convoluted, while the Chesi is straightforward. And from the Chesi, you could get over here, which is even further, more straightforward than Chesi. I found about this equation from my professor, from Daryl Simons. But unfortunately, he used a variation on this equation. Not this equation, but a very slight variation, I must say. Instead of using f, she used square root of g over c, something like this, which is the same, by the way. At any rate, that's another story. I think I already talked about that before, if not here in some other class. So, it is concluded that the inherently stable channel will never achieve the asymptotic fruit number. We already said that. Assume a realistic maximum value, fruit number equal to 25, and then we have a conditionally stable channel. So we have the inherently stable channel in here, which is repetitious from what I've already said. Triangular, okay, we have the hydraulically wide, I'm sorry, and we have in here, I believe we can click in there and we get there, right? Or we can have the triangular, we click the triangular and we get the triangular. We can do that marvel with the web. And then the inherently stable. And all these equations have been repeated already. And then we came up with this equation or the state formula or table for selected parameters. The fruit number for neutral stability from 3 to 10,000. 3, we don't use 2 because 2 is 0, right? So we started at 3, 5. The beta, 1.33, and the beta starts coming down. By the time we get to infinity, the beta is 1. The delta, 0.5, and then it comes down to 1. Conditionally stable, strongly conditionally stable, quasi-inherently stable. And we came up with a calculation of the factor of safety, by the way. Where for the conditionally stable, it would be 1, and here less than 1, and here greater than 1. We can go to the definition of the factor of safety. We try to get a little bit more on the category of design, and when you talk about design, you're always talking factor of safety from an engineering standpoint. So we wanted to add that in. This is the first time people had ever done this. And then we get into the stable channel design, and this is tough. This is really tough. Because we're explaining here how we did this calculation. It's an integral and so on and so forth. We have the input data and we have then the recursive procedure. This is a digital numerical procedure, which is a recursive procedure. Recursive procedure means that you don't advance, you iterate until it finishes and then you advance. It's like Heck-Ras does that, by the way. But they do it so fast, you could not believe the speed of Heck-Ras. Those of you that are going to run Heck-Ras, it goes like in 1 second, that's it, the answer. Why? Simple. They use Fortran. And Fortran is the speed of light. Fortran operates under the speed of light. That I know. I happen to know because we've tried it so many, many times. We have a hard time finding an algorithm that will be in Fortran slow enough for us to say, we're going to go to the bathroom and come back. No way. It's usually 2-3 seconds maximum. No time to go to the bathroom. Okay? I'm joking, but that's the truth. So the recursive procedure is over here. So if you're interested in how this was done, we spelled it absolutely all out for you. You can do this stuff if you wanted to. I don't see the need for it, but you can do it with Excel because you already have spelled all out. Everything, every step was spelled out. And that's what we like to do, by the way. We got to spell things out so that people can understand where it came from. We are not selling anything. We really are not selling anything. If I was selling something like in a consulting firm, I wouldn't do it, to be honest with you. But I'm not in a consulting firm. I was already paid fully by the state. So we are here to benefit the state of California, the people in California, and so on and so forth. So we're not hiding absolutely anything. All the stuff was out there extremely, look at 26 states, 26 steps, recurrence. And finally, we got the online calculator. We got 5 minutes here. The online calculator solves a recursive algorithm explained in the previous section. Consists of geometric and hydraulic data. The half bottom width, we're only designing half bottom width, by the way, not the whole width, because half bottom width is symmetric. The depth, the side slope, the relative depth, h sub u prime, the channel slope, and Manning's, and the neutrally stable. So in here, I'm going to run it for you, so you can see how this thing works. First of all, I'm going to tell you a story, an interesting, fascinating story. I say table 2 shows a summary of the output. And here I have a Fortran file. You're going to laugh at me. Professor Ponce still using Fortran. And the answer is this. I commissioned Marcela Diaz, to do the PHP program. But he was a rookie. And I said, short of getting in there and redoing it for her, I'm not going to be able to follow. If she makes a mistake, I won't be able to find it. And she probably won't either because she's a rookie, she's new. So I said, simple, Marcela, you do the PHP and I do the Fortran. You can take a month to do it. I will do the Fortran in a day because I know I can do it because I'm fast. So that's exactly the way it happened. She did the PHP. It took her probably a month to do it. And then I sat down to do the Fortran. It took me a day. And then we ran both under the same data. And you know what? You came out with the right answer. I used my Fortran program to measure the correctness of her program. And that was the right approach. Otherwise, I would spend months trying to figure out where she made a mistake. Not months, but a few days, I would say. No, she did well. She was good. Okay? So now I'm going to run this model. I'm going to run this model with this data. In order to do that, I'm going to have to get a little smart in here. And I'm going to go like this. I'm going to go like that. Okay. Okay, I'm going to try to move this stuff. Oh, yeah, I can move it out. Okay, so I'm going to need all this data here, okay? So in order to do that, I'm going to say, where is it now? I'm going to go a little, I think this is it. Half width 2.5, okay? So half width is going to be 2.5. Then depth 1 and side slope 0. Depth 1 meter of the bottom part, side slope 0. Okay, the relative depth, which is the depth on top, that's the top of the overflow channel. The relative depth is going to be over here, 1, the slope 0.012 and 0.015. So I'm going to go in here, back in here like this. The relative depth is going to be 1 and 0.012 and 0.015. Okay, what we want in here is to, if I understand this correctly, okay, where's the discharge? I get lost in here. Well, the discharge should be 20 at 100. I just don't know exactly where I put the discharge in here. I just read it this morning. Well, let me run it anyway. Okay, I'm just gonna increase the accuracy. Okay, we're supposed to run 10 on the bottom channel and 100 on the top channel. Okay, it's somewhere out there. I saw it this morning. Okay, there it is. There it is. There it is. Yeah, 10 and 100. Half bottom width. Okay, so I use the numbers in here. Okay, calculate the h sub o. Yeah, everything is fine. The h sub o is equal to 2. Oh, I see. There's a mistake in here. There's a mistake in here. the h sub o is equal to 2. For the, okay, the h sub o is equal to 2. H sub o equal to 2 means that the depth of the higher channel is twice as much the depth of the lower channel. Okay? So now, over here, on the right side, we're going to choose what's the Fruit number for neutral stability. So the first thing I'm going to do is I'm going to do an inherently stable channel. The Fruit number is 10,000. That's huge. In the upper lines, say 20. Upper lines gives me a resolution on the table, on the result table. So what do we have in here? This is an inherently stable channel. Therefore, the hydraulic radius should not vary with the stage. That's the definition of the inherently stable channel. So look at the hydraulic radius, 0.714, 0.7, that's a nice number, by the way. Mathematically, it's a nice number. So it's all the same, so it's correct. This calculation is correct. It's a PHP calculation. As far as the flow is 14 for at the top of the bottom channel, at the top of the base load channel, and 172 at the top of the higher. So it's roughly what we want. Okay, so now, and the reason why I say that is because let's now put in here 25. 25 is the one that we're going to design for conditionally stable. And we're going to do, again, this calculation. And you can see in here that now the hydraulic radius is varying, right? Hydraulic radius is not varying as the way it should be. And the half discharge is 14, which is close to 10. And over here is 155, which is close to 100. So you can play around with this calculator, play around with the numbers. If you want to zero into 10 and 100, so be it. But there's no need. We already shown that this thing works, and it works fine. So that's basically what I was going to do today. So how about that? It's 6:45. We ran out of time, and we precisely finished this. So I urge you to review this. Don't spend a whole lot of time in the math, but emphasize the concept. You need to know the concept because the concepts is what's going to be on the exam. Okay, so now at this point, all we have left in here is to do, let me see this. If I close tabs in here, I'm going to die. Okay, fine. Let me just say we ended this. Thank you very much. Any questions? Like I said, I reiterate for the end time. If you have any questions about anything related to the class, you just get a hold of me.